I wanted to talk about a potentially difficult subject today. I wanted to talk about something that is maybe a little embarrassing and a bit of a dirty secret for many computer scientists. It's not something we normally talk about in public. It's not something we normally talk about here in academic classrooms, but it's something I find a lot of you doing late at night by yourselves in your bedroom. Sometimes it's okay to do this to a small extent. It gets more worrying if you're spending many hours a day doing this. I've even caught some of you doing this for many hours a day in the workshops and in offices. And that's when you know you have a problem, if you're really doing it to that extent. And this is debugging. Okay? When we talk about software design, we talk about these great big academic concepts. We talk about great big ideas in language design and so on. We still find a lot of computer scientists spend the bulk of their days doing this rather than actually creating the software. So what I've done here, I hope I'm going to enjoy this lecture. This is all the stuff I wish I had been taught 20 years ago that was never discussed in academic settings. I want to really get into these dirty details of how the debugging processes work, but more importantly, how to avoid having to do debugging in the first place by doing other kinds of processes that can prevent it from even happening. So I really hope you'll take this away, and this could potentially change your lives. It could change the bulk of the way you spend your hours as a working programmer if you get this stuff correct. So today I'm going to talk about two classes of tools that can help you with this. These are static analysis tools and dynamic analysis tools. Okay? Static tools are things which take your program text as input and they inspect the text of your program to make inferences and deductions about it, which can help you to prevent these things from happening. So you're probably all familiar with compilers already. Maybe some of you are familiar with linters. So a linter is a little like a compiler, but it takes your code and it effectively gives you a whole more things like the warnings that come from your compiler. Sometimes your compiler will give you errors and say, I'm not going to compile this. Sometimes it will compile it, but it will give you a warning and say, hey, maybe this is a bad idea. A linter is like a compiler on steroids. It will give you many, many more warnings about everything. There are also tools you can use to extract documentation automatically from your programs to help you see what's going on. Language servers are another compiler-like system that will sit in the background and try to analyze what your code is actually meaning. We'll talk a little bit about verification. This is the idea of proving whether or not your programs do what they're supposed to do. So these are very computer science-based tools. They operate on programs. The fundamental principle of computer science is that we study programs as objects. Okay, mathematicians study numbers. They prove things about numbers. Computer scientists study programs. We prove things about programs. And static analysis is all about studying programs as objects. Then we get to dynamic analysis. These are tools which study your code by actually executing parts of it rather than just looking at the text. So testing is a big part of this. This means executing small chunks of your code to see how they behave. I'll talk a little bit about contracts and contract-oriented programming as a generalization of the testing idea. Then we'll come to the really dirty stuff, which is debugging. The moral of all of this is don't get into this stuff unless you really have to. Debugger is your last resort if none of these other tools have worked out for you. And there are other kind of dynamic tools like memory monitors and profilers we can talk about as well. Profilers are for making your code go faster. They help you to optimize the design. So let's begin with static analysis then. You're probably all familiar with a compiler. A compiler takes source code in some high-level languages input. It goes through several stages to process that code to make it executable. And the first stage of that is parsing. That means looking at the text in the high-level language, understanding it, and making sure it's okay. Within that process, there are many types of error detection that a compiler writer might choose to build into their compiler. Okay, some of these are really necessary for the compiler to work. Others are there just to help you as a programmer, to give you warnings about things that you might consider doing differently. So most basically is the detection of syntax error. If your program doesn't compile with a regular compiler, we'll talk about other types of compiler shortly. If your program doesn't compile, you obviously know that something is wrong. So at the level of syntax, this is basically checking that your program is a well-formed piece of text that can be converted into some structure similar to these Scratch programs. I'm teaching Scratch in junior schools at the minute, and it's an amazing language. One of the reasons Scratch is an amazing language is that every program that you can write in Scratch will work, in a sense. There's no such thing as a syntax error, because Scratch actually forces you to build the parsed structure of your program. So there's no concept of a syntax error. If you can actually make your program in the GUI, then it's going to work in some sense. Other types of errors, then a compiler may be able to catch arithmetic errors. If you do something divided by 0 at the level of text, a good compiler may be able to catch that and give you a warning. Many compilers include type checking, so they understand every function takes inputs of certain types, and if you try and call a function with something that isn't a member of that type, it will give an error. Not all compilers do that. Some languages have very heavy type systems, some have very weak type systems. And some compilers will try and help you with memory. If you're using low-level languages, C-style languages that give you access to the memory, there are many bad things that can happen when you try and reference memory that you're not supposed to, and a good compiler will be looking out for that and giving you errors and warnings about it. Some of these will stop your program from actually compiling, some will just appear as a warning. The other kind of warning you'll often see, especially if you're a Java programmer, do we still have any of those? Maybe not so much now. You may get warnings about versioning and depreciation. Java is famous for constantly updating all its libraries, and compilers giving you warnings saying this version of a library is going to be retired in 6 months. So these are the kind of static tools that you're probably already familiar with. Then when we get to linters, a linter is usually based on similar code to a parser from a compiler, but it will behave in a somewhat different way. The job of a linter isn't to convert your code into assembly language. It's merely to check the code and to look in more advanced ways for different types of errors that could be sitting in there. So when you run a linter, this is a separate program. This exists outside of your compiler. Again, a lot of these will look for things to do with memory. There are known bad ways of writing programs in many languages that are sometimes called code smells, and these code smells can be detected as very well-known things. So there are things to do with memory that may be bad. There may be just particular styles of coding that the author of a particular linter decides are good for you. So, for example, you might be working in a language that isn't very object-oriented, like C, but your team may have decided we're going to program in an object-oriented style. So you could build a linter sitting on C, which checks that all the code is being written in an object-oriented style and is set to moan whenever you deviate from that. Similarly, you may have coding standards, things like tabs versus spaces in your Python code, naming conventions for variables. Are we going to start everything with a capital letter, with a lowercase letter? All these things can be programmed into a linter, and the linter can be made to complain loudly when any of these things are violated. And then you know who to blame on your group project if something is violating a convention. So linters are often used to compensate for what their authors perceive to be design flaws in the language. Okay, if you had a perfect language, you wouldn't need a linter because everything the linter's doing would already be built into the compiler and it would prevent you from doing those things. The problem is that no two people in the world can agree on what is good or bad coding. And so what you find is for most language, there are many linters out there which compete with each other, and they all enforce different ideas of what their authors think is good coding practice. So some of these things are less controversial. If you're doing things in your code that are obviously going to make an error throw, like referencing a piece of memory that you obviously shouldn't be touching. Other things are very subjective around coding standards, naming conventions. So this is something you can do now in your group projects. You can consider whatever language you're working in, go and find out who is currently making linters for it and run it on your code. And some of ththese things will complain about every single line of your code. Okay, when I prepared this lecture, I took some of my old Python code from a robotics project and I ran it through PyLint, I think, And pretty much every single line of my code, it found something obscure to complain about. So there are different degrees of subjectivity here. Another form of static analysis is to do with documentation generation. If you do this, it can help you to understand your own code and the code written by other members of the group. And it saves you the effort of manually writing documentation, which would be very error-prone. It makes sure that the documentation is always synchronized with what's actually in the code. So you will get these static analysis tools, which again take the text of your program as an input, and in this case they're going to convert it maybe to an HTML web page like this, maybe to a graphical display. This is from the program PyReverse, this is from Doxygen. And what you see here is that the documentation generator has gone through the code, it's pulled out all the feature signatures, or at least all the public ones, all the things that you want users of your code to be able to see. It's extracted some of the comments, maybe the comments you want to appear in the generator have some special syntax to distinguish them from comments that are just internal. And it will generally make a nice HTML system where everything's linked to everything else. So if your class cat is going to have a hello method that takes another animal as input, you'll be able to click on that and it'll take you over to class dog on the HTML system. So again, this is a nice way, this is something you could do now. You can run these programs like Doxygen on your group project code and make nice automated documentation. When you view it in this form, this is UML language. Anyone seen this before? Yeah. This is just a graphical notation for object-oriented languages. Every class in your program gets a little box, and the dependencies between classes are shown by arrows. So this is how we allocate your group projects. Okay, we use an algorithm and a program written in Python to get everyone in the right groups with the right supervisors. So this is what I've extracted from that Python code. So you can see we've got class group. A group has 6 members in this case who are students. Each student has a preference for the project. Each student is on a degree program. Each project has a supervisor and so on. So again, this is a nice tool, especially if you're working with other people's code and you're trying to understand it. You can quickly run this and see an overview of how everything's fitted together in the code base. I would not advise drawing these first. Okay, when this style was when UML was first created, it was part of this old-fashioned waterfall model of software engineering where you were going to design the whole project using notation first and then go off and implement it. You might as well just create those classes in Python, even if the methods don't do anything. It's just as quick to write out the frameworks of those classes and run the documentation program to generate this nice figure. And that has the advantage that your code is now synchronized correctly to the documentation. So that's why this thing's called PyReverse, because traditionally it used to go the other way. But now it's seen as a better thing to go in this direction. Language servers are another form of parser-based static analysis. Your parser inside your compiler is usually very exacting, and if your program doesn't fully compile, the thing will just break and stop, and you need to go and fix the errors before you get any useful information beyond that. There are a different class of parsers, which we will call partial parsers, which are set up slightly differently with the intention of understanding code fragments. Okay, so you can take a piece of code like this. This is my Vi setup. You can see I'm in the middle of writing this code. So this code does not compile. Okay, this is saying T dot. That is technically a syntax error. So if you give this to a regular compiler or interpreter, it will just barf and say this is not legal code. If you give this code to a partial parser, it will do its best to understand what is in the code and to make some sort of educated guess about what this thing is going to be part of. So a partial parser can suggest ways of correcting syntax errors if there's something wrong, or if there's something obviously missing, it can suggest what you might want to type next. And this is called auto-completion. So when I showed you my Vi setup the other day, I pressed a key and I got this list of auto-completion options. What this is doing then, it can see that T is a tiger. Okay, tiger is a class, T is an instance of that class. And when I type T dot, that is going to trigger this auto-completion module. to go and contact the partial parser, and that parser is understanding to as best extent it can all the code that I've already written, and it's then going to give me suggestions, so I can say T dot, and it knows that these are all the things that live inside class Tiger that I might be about to type. Now, until about a year ago, this stuff was very, very murky indeed. Lots of competing standards and really not talked about very much at all. What we've seen over the last year has finally been some sane unification of it all with this new standard called Language Server Protocol, or LSP. So LSP is a standard way for clients and servers to talk to each other. A server is a partial parser. So in this case, I'm running a partial parser for Python. That's sitting in the background of my computer, and it's kind of cognating about all the Python text that it can currently see. It's running as a process, thinking about that code all the time. The language server sits there, and then the client, so in this case I'm using Vi. You can get clients for all your favorite other editors. The client will then connect the text editor to that same server sitting in the background. And so what happens here, when I type in T dot, that's the trigger for my Vim client to go and ask the language server what's going on. The language server is constantly building up this model of what it thinks I'm typing about, as a compiler would do, but with partial parsing. And when I type that dot, the client goes and asks it, what do you think is going to happen next? What do you think the programmer is going to type following that dot? And it will then send back to the client a list of all these possibilities. So other things you can do with language servers are things like auto documentation display. So for example, this window here has popped up in my Vi to tell me something has guessed. Okay, here, look, I've selected hello as the method I want to call from Tiger. And again, that has gone off and talked to the language server, and it said, tell me some more about this method hello. And that gets displayed up there. So in this case, there's not much to say. It's just given me the signature for that function. If I put in loads of documentation or comments or type information, all of that will just pop up along with everything else getting displayed inside the text editor. So traditionally, this has been a mess because every editor needed its own language server. So you have a matrix of every editor versus every language, and you need a lot of implementations. What we finally have now is this one protocol called LSP, where every language just needs a single language server, and then every text editor can connect to the same language server, and everything suddenly gets a whole lot easier. To give credit where it is due, this is an open source innovation from Microsoft, who were traditionally not known as an open source friendly company at all. This is something they have given, apparently, to the open source community that is working very well, and we are very grateful for it. Let's see what happens. Let's see if it gets extended and extinguished in a few years. Yeah. Okay, so the final type of static analysis I want to discuss, and this is only going to name the surface of an iceberg. There are whole degree programs in theoretical computer science around this, is the notion of formal methods and verification. So these are tools which try to prove that a piece of code actually works. What do we mean by actually working? This could generally mean one of two things. One is that it is immune to certain classes of error. So for example, you might like a tool, a bit like a linter, that you can run on all your source code and it will detect, is there ever going to be a memory leak? Can you prove that this code will never leak memory? Okay? Can you prove that it will never throw certain types of exceptions, that certain types of memory will not be referenced when they're not allowed to be? The other type of proof you can do is to do with the function of the code. This is to do with proving the code will not crash. This is to do with saying the output is what you actually want it to be. And this is where it gets much harder, because now you have to specify what you want the piece of code to do. So say you've written an add function, takes two integers as input, gives an integer as output. You may wish to prove formally and mathematically that the output will always be the integer sum of the two inputs, and it will never be anything else. So you can't do that with testing, because in a test you can only test a finite number of cases. If you prove it, this has got to work for all possible inputs. We sometimes say for all by writing a big upside down letter A. That means for all inputs. There's a lot of real computer science here. Okay, you guys don't really study much what I would consider to be computer science. You study a lot of programming and building things, but formal computer science means studying programs as objects, mathematical objects, and proving theorems about them and understanding their behavior and their properties. So there is a whole world of this stuff out there, okay? There are limits on what can be proved by formal methods. This is the reason they don't often appear in the real world. So if we go right back to Alan Turing and to Church, some of the first results they proved were these negative results, saying some of these things cannot be done. You cannot build a linter, for example, that will test whether or not your program halts. Okay, especially in robotics. I'd really like an infinite loop detector, because some of our robots crash and they just freeze up and stand there. That can be very dangerous. I'd really like an infinite loop detector that will find if there's any possibility that the program could just get stuck in a while loop and freeze up like that. But it's mathematically provable, as shown by Church and then by Turing, that you cannot build such a linter. Okay, that program does not exist. It's an uncomputable function. But it's not the end of the world, because there are some circumstances where you can do this. So Church and Turing's results are only for the general case, okay? And the way they're proved is by considering some very obscure programs indeed that are deliberately created to confuse any potential linter that tries to run on them. So if you're willing to restrict the world of programs you're writing to things that are not deliberately pathological like that, you can get much further with this. And so we're now seeing a new wave of these programs. In your favorite text editors, your linters, your IDEs, we're starting to see more of these automated tools come in that will try and detect this kind of thing in limited cases. So we can prove they won't always work, but they might be helpful in some cases.
Create a linter that would prove or detect whether or not your program was within the subset of programs that did provably halt it?
I can't prove it, but off the top of my head, almost certainly not, because that's usually how these proofs end up going. Yeah, third year project for you. Yeah. Okay, so you also find these ideas showing up in language design itself. There's a duality between what is here called software engineering or software creation and language design, okay? One man's software engineering feature is another man's language design feature. And what we've seen through the whole history of computer science is this process where object orientation gets created as a software engineering practice. It's a way of writing programs in C or whatever, and then the language designers pick it up and say, we'll just build that into the language itself. So what we see now in more recent languages like Rust in particular has really thought about these issues of memory safety. There used to be a whole bunch of very theoretical computer science ideas that could be put into these linters and memory checkers to prove when things were memory safe or not. When you go to a language like Rust, they now try and bake that into the language itself. So Rust has very particular memory management rules, which look kind of crazy when you first see them, but they're very theoretically justified. There are reasons why these particular types of memory access are allowed or prohibited that follow from this kind of formal verification approach. Something else we're starting to see is what's called invariant detection. We'll talk later about contracts in general. These are things that you can do as a programmer. You can make claims that certain things will not change in your program. Okay, if you say variable x is invariant, that means x is not going to change its value, or the sum of x and y may be invariant. And again, some of these tools are starting to try and do this for you now. Instead of manually going in looking for invariants and putting them in as assertions, you can run tools that try and create the invariants and add them to the code for you. Now, what's interesting about this specification idea is that traditionally this has not worked out so well, because when you try and specify what your function is supposed to do, this can get very, very complicated in itself, right? Imagine you're writing even an addition function, okay? You may say, my specification of this function is it takes two inputs, x and y, and it adds them together and puts them in R, okay? Is that really the specification of an addition function? What could go wrong with that? Give me some things. Yeah, the numbers could be too big. Is this going to be defined on 32-bit ints, 64-bit ints, or do we actually require it to run on some real int that can keep growing and growing? Anything else?
That was pretty negative.
Yeah. It doesn't specify if they're negative or complex or quaternions or weird mathematical structures that can also be added. Or what does it mean to add two vectors together? Does that mean to concatenate them? Does it mean to add them element-wise? So what tends to happen is people have tried to build these very formal specification languages using logical symbols, and you can end up writing specifications that are much, much longer than the programs they're actually specifying. Okay, your program could just be y equals a plus b. That's the whole of your addition function, and you might end up with a whole page full of logical specifications. Another interesting question here is if you've done that, all the information about your program now appears to be in the specification. So why bother manually writing the program? Okay? Why not create an automated tool that just takes the specification and turns it into a program for you? And that's exactly what you get in functional programming. You can, for example, write a function in assembly language that will add up all the numbers in a list. And you can write a functional specification that asserts that the sum of everything in the list is going to be the sum of the first element in the list plus the sum of the rest of the list. And if you just write that specification into a functional programming language like Haskell or ML, then it will automatically compile that into the imperative assembly program underneath. So again, there's this duality between software engineering and language design. Every time a great idea comes up in software engineering, like specification, the language designers will jump on it and they'll just pull it into the language. We talked a little bit about the similarity between software engineering and AI, right? AI has this problem that whenever it works, it isn't considered AI anymore. Okay, so sometimes AI is described as all the bits of computer science that don't work yet. But there's something similar going on here, right? Software engineering has a bad reputation as an academic field for suggesting things that don't work. But when things do work, like specification, this is what happens. They get jumped on by the language designers, and then they're not part of software engineering anymore because they've been pulled inside the language. Okay, so that's a quick overview of static analysis tools. I hope some of these are actually useful to you right now doing your group projects, okay? Why not go home after this lecture and try running a linter on your code? You could try running a documentation generator on your code. Formal methods are a little harder. I probably wouldn't advise that at this stage. Certainly good things to put in your assess group reports if you show you're using fancy tools like these. But normally when we think about the debugging process, we are thinking about dynamic analysis, as in executing programs or parts of programs. So this is not just about running debuggers. Dynamic analysis also covers the testing process. So we've had a couple of speakers in the series talk about unit tests already. I'll tell you a little bit more about unit testing now. So testing is a form of dynamic analysis, right? As opposed to static analysis, which operates on the text of your code, dynamic analysis actually executes parts of your code on a hardware machine. Now, we need to be careful with testing because unlike formal proof and verification, program testing can be used to show the presence of bugs, but never their absence. Okay? So say you've written your addition function again, takes two inputs, makes an output. You can write as many tests as you like. You could say check that 2 plus 3 equals 5 and 1 plus 1 equals 2 and 0 plus 0 equals 0. You could spend days and weeks writing hundreds and thousands of these tests, but you will never be able to cover everything. In a formal proof, you prove things for all inputs. You have this upside down A, meaning for all. But with testing, you're only ever going to get a sample. So there are still bugs that can sneak through. You can have all the tests in the world and still the possibility of a bug sneaking in. How not to do testing. This is the traditional waterfall software engineering method, which I do not recommend to anyone. This is the process where you go through requirements gathering, you finish that, then you spend a couple of months doing design, then you spend a couple of months doing implementation, where you magically build a piece of software, and then when you finish doing that, then you send it over to your dedicated QA quality assurance testing team, and their job is to spend 2 months doing testing to let you know if it works or not, and then you release it. So there are all manner of problems with this process. We've had a lot of speakers in this series come in and talk about this now. I think everyone we've had in prefers this agile methodology where you have very fast iterations of all of this happening together. You go round and round and round, you do a bit of design, a bit of implementation, a bit of testing, continually feeding back on the process. So what is meant by testing nowadays, usually, is not this send it all off to QA at the end of the project. Okay, what is meant by testing now is an integrated part of the software creation process that is probably done by you as a programmer rather than by some dedicated QA person. And it is usually based on this concept of unit tests. Now, unit is a funny word. I've struggled to find out where this actually came from. Typically, when we talk about unit testing, we mean either a class in an object-oriented language or a module in a non-object-oriented language. A unit just really means any distinct chunk of code, anything that might all come together in a file or in a class or some other kind of sensible grouping, regardless of the style of language you're in. And the idea then is that each of these units that already exist in your code, such as the classes, are each going to get their own test corresponding to them. Okay? And the hierarchy of tests is going to mirror the hierarchy of code. So this is a UML diagram of one of my projects. This is a music composition system, automated music composition. And you can see it's based around a class called notes. This is a musical note which has a degree and a scale. It has a key, a duration, and amplitude. The note can then be split down into its constituent parts. So key is also a class which has information about the scale and the tone. The degree is a number within the scale, whether it's sharp or flat. And these things are all based on rational numbers. It's all based on fractions with a numerator and a denominator. Notes fit together in a score, which is the piece of music. So what you see in this diagram is that it's been extended to show the unit tests. So in this program, each one of these classes has a corresponding class which has the same name but with the word test stuck on the front of it. There are different ways to set this up programmatically. This is just how I happen to do it. So you can see at the lowest level I've got a bunch of test functions in here that are going to make sure that my rational number class is working. So I need to be very confident that I can create fractions, I can add them, I can multiply, I can divide. And each of these little functions in the test rational class is going to call a bunch of basic things, add 1/4 to 2/5 and check that the result is whatever it's actually supposed to be and give an error if that thing doesn't work. So once I'm happy with that, then I'll go and build a test for the next thing in the hierarchy. So key is a higher level object. It's depending on some other classes. So there's some quite complex tests in here. Again, I'm testing various operations on the key. What happens if I transpose something? What happens if I shift the scale patterns? What happens if I try and create a key with a bad input string? How's that going to get handled? Then when I'm happy with that, I'll do note. So again, test basic things, test some harder things, and then I'll test the whole score at the top. Now, I don't always know what these tests are going to be in advance. Often these tests are added in response to a particular problem. So I might have built all this stuff first, and then I find a bug, and during the process of trying to find that bug and fix it, I will be creating new tests as I go along, because I want to make sure certain things are happening the way they're supposed to happen. I mean, some people like the idea of building a whole load of tests anyway every time they write something. Personally, I find it's a bit of a waste of time because sometimes my code just works, and it would be a waste of time building a load of tests for something that is obviously just working. So personally, I tend to add these things in response to every bug hunting round that I'm involved with. Some people prefer to write the tests first. Okay, this is called test-driven development. You write the whole set of tests in advance, and then your job, or often the job of someone you delegate it to, is to write some code that can go off and pass the tests. So, again, this is something you can do now. This is something you can do in your group projects. You can write about it in your reports. Good way to get some credit using some proper software engineering methods. You don't need to use any special libraries to make unit tests. Okay, I did this without using any test libraries at all. I just created a bunch of classes, and each class corresponds to a class in the code, and it's got a bunch of test functions, and I call them one at a time. However, most languages nowadays will give you some kind of lightweight library that will just automate a little bit of that. So, for example, in my code, I have to manually go through and call every one of these test functions that exist, and a nice test library will do that for you. It will know that these things are test classes, and it will know they have a bunch of functions, and it will find them and call them automatically. So you'll often find this kind of structure. There'll be a class in an object-oriented language. There'll be a class called unit test or unit or something like that, and then you will extend that class with your particular form of test, and through that extension process the system will track where all the tests are and be able to come around and call you. This is actually an example of a type of design pattern. We might talk about design patterns a little later in this module. So, when I was a student, this was actually drilled into us a lot back then, and we did it properly because we were using very strongly typed, compiled languages like Java at that time, where you really had to do this. I have fallen into a bad habit since then because I've switched to using interpreted languages a lot, and if you have an interpreted language like Python, it's very easy to just run your own quickly interpreted tests direct from the command line. So for a long time I was writing function. I'd write my little add function, and then I just test it immediately on the command line. I just say add 2,3 and check the result was fine. That's kind of great until 20 years later when you have to get your code out and make it all run again. So as another part of this module, I've been running an experiment. Okay, I've taken my own undergraduate project, like you guys are doing now, 20 years ago, and I'm trying to make it run on a modern machine. And it's all written in Java from like 1998, and it uses all these funny libraries, and there's a lot of work that needs to be done to maintain it and to bring it back up again. What has been very interesting from this experience is that all this over-engineered software engineering testing-based junk that we laughed at the time, we thought we were just building all these unit tests to tick some boxes to get credit for our degree, so we did it all very properly. All this stuff is actually really, really useful. So I've now got all these tests in a nice script from 20 years ago. I can see which ones are passing and which ones are not, and it will take me very quickly to the things that need to get upgraded. Okay, so in particular I found, this is a music project, it's parts of the MIDI system have been updated in later versions of Java. But because I've got 100 of these tests all in a file, I can see which ones pass, which ones don't, and it takes me straight away to where the thing is. So the advice I'd give, if you're working with interpreted languages now, if you're doing this kind of numerical data science hacking style programming, you can still write your tests out the command line. You know, I still do this. I'll write my add function, I'll type add 2,3, I'll look and see if the result's 5, but then after that, I'm going to take 3 seconds, I'm going to cut and paste that test out of my command line, and I'm going to put it in a big file that's full of tests, and I'm going to keep it forever. Okay? Every time I fix a bug or test something, I'm just going to spend 3 seconds putting in that file, and it's going to build up hundreds of these things in a file, and then in 20 years' time, when we want to run that code again, which we might very well need to do, it's going to make life massively easier. Okay? So here's an example of how to actually write tests. In this case, it's Python. Okay, so look, two very simple functions, taking an input, returning an output. Here I'm creating a test class corresponding to that thing. So this file's called myfunds, that's the unit, this is the test file corresponding to that unit. Okay? So in this case, I'm using Python's unit test library. I extend the Python unit test class, and this is what a test actually looks like. It's a little function Usually it's called test underscore then whatever the function is you're testing, maybe with a bit more detail in the name as well. And I'm using these assert functions. So an assertion just makes sure that something is equal to something else, and it throws an error if it isn't. So here I'm saying go and call function with the number 3 and make sure, assert that the output of that is 4. And if that doesn't work, I'll get a clear error message saying where the problem is. So this is a smallest example. You could imagine this containing hundreds of test functions, all for this unit. You could test hundreds of different inputs and outputs and assert on them all. So testing doesn't stop there, okay? The dream of this is to get fully automated debugging. We would really like to not spend our days in an office searching for bugs. We'd like to press a button and say, find the bug, okay? And there is serious research going on now about how to do this. And it's based around this concept of delta debugging. Anyone seen delta debugging before? No? Okay. Okay, so this is based on the manual process I told you about. This is how I actually fixed my 20-year-old Java code. So I have this set of tests, and I'm colouring them red and green to say which ones are passing and which are failing. Okay? The tests exist in a hierarchy that mirrors the hierarchy of the code. And when I run this set of tests, I can see a pattern here. I can say this is where they stop passing. Okay? There's a point in the hierarchy where things start going red. So this tells me that the problem must be here. I know everything on this side of the line is good code, and something around here is the problem. This instantly tells me to go and look in the node class and start inspecting them. So if you've written a good set of unit tests, there are tools now that will automate this process. You're trying to find a bug, something is causing the program to go wrong, you automatically set off this tool, it runs all your tests, and it will home in and find out exactly where is the dividing line between the green tests and the red tests, and then that's where your bug's going to be. So you can then go in at an even lower level. So this is automated debugging at the unit level. This will find the unit that is red. The other part of delta debugging then is automatically finding the line where your bug is coming from. So I'll talk in a bit about the universal fix-all algorithm. Okay, this is how I usually debug your tasks in workshops if I haven't read the workshop myself. There's a universal fix-anything algorithm. This applies to real-world engineering as well as computer programming. So the fix-all algorithm is you have two versions, one that works and one that doesn't, and you gradually change them both to become more like each other, and when they only differ by one little thing, then that's the thing that's causing the problem. Okay? You can fix anything, motorbikes, central heating systems, whatever, using that algorithm. And that's what you get in these automated debugging systems. They will automatically create thousands of versions of your code with different lines removed. They'll maintain one version that works, one that doesn't. For example, from your source control system, it will pull out the latest working version, and it will automatically home in and find the single line that is the source of the problem. And that's called delta debugging. Okay, so another idea I've got excited about in my own software engineering practice recently is what is called contract-oriented programming. A unit test is, in this view, just a special case of a more general concept called contract. Especially when you're working with other people's code. Okay, nowadays no one writes code from scratch on a blank screen by themselves. Every piece of code is calling someone else's code somewhere. And unfortunately, other people's code doesn't always work, at least in the way you think it's going to work. So, here's a great piece of advice for the rest of your working lives. I wish someone had told me this a long time ago. Whenever you take someone else's library that you're planning to use, anything you've downloaded, you're going to call functions. Before you do anything, you're going to get tests set up on the thing. If it already comes with tests, as a lot of things do, you run the tests. And that set of tests forms a contract, okay? Any function in those tests that is passing, you now have reasonable confidence actually works because it passed the test. If there's a function in someone else's code that does not have a test, then do not believe anything at all about it until it passes the test. So if there's something in there that is undocumented, doesn't come with the test, then you create a test, you write your own wrapper for it, Keep track of them, and that will serve the same purpose. Anything that passes your test is now reliable, and that means you're allowed to use it in your program. If it's an open source project and you've written a new test, you should contribute your tests back. And you see some of these projects now have long lists of thousands of tests that all their users have contributed together. So one idea I'm excited about is combining tutorials with this type of contract-based test. When you download an open source program and it comes with a tutorial, often the tutorial has gone out of date, the code has changed, no one's updated the tutorial. What we're starting to see in a few places now is an integrated online document that is a mixture of a tutorial and a set of unit tests. Because when you think about it, a tutorial document is a kind of contract. It's saying, these are all the things that the program's supposed to do. Here are all the examples. All these examples are supposed to work in the code we've given you. And that's exactly what a set of unit tests is also doing. Okay? So think of all the examples in a tutorial document as unit tests. So this exciting new idea is that we formally merge them together. Okay, we create a language a bit like Markdown or like a Python notebook or something, which is going to be an interactive tutorial document. And the tests just are the tutorial examples. You arrange them in a nice order to be educational for the reader. And again, it won't guarantee everything works because a test can never guarantee anything, but it will give confidence that all the functions that appear in that tutorial or set of unit tests work. Conversely, you will often come across open source projects which are lacking a tutorial document or appear to be lacking a tutorial document. So this happened to me the other day with Rope refactoring library for Python. Sometimes the authors will assume that you know about this. They'll give you a whole load of unit tests and they assume that that is the tutorial. So if you come across a project with no tutorial but a load of tests, it's very possible the authors intend you to manually work through those unit tests as the tutorial document. So before you go whinging there's no tutorial, go and look at the unit tests as well. So that your programming lives will be infinitely better if you follow this advice, right? Never call someone's untested function. The major cause of aggravation in modern programming, as distinct from 1980s style programming, is that we now rely all the time, every day, on other people's code. And when that code doesn't do what we think it does, that makes us very angry because we like to be in control of our system. So if you follow this rule, you can completely obliterate that problem. You make sure everything you're calling that's written by someone else has been wrapped in a test, and then you can be a very happy person. Because if the thing doesn't work, you can now very clearly say it's your fault. And you can, if you're feeling generous, you can fix it and send them a pull request and get it updated. If you're less generous, you can just whinge at them and send them an issue and ask them to fix it. So these are some examples from that project. This is something I was setting up the other day. So you'll see, this is the documentation for the Rope project. It's a series of tests and it just takes you through everything that the Rope library can do. And it's intended to be read and run by you as a human. This is the tutorial. You run each of these, you'll learn exactly what Rope is doing. So these tests are also useful when you're working in a team environment. In all of this, I distinguish a team environment from a community environment. Community is open source world where you don't really have any control over what everyone else is doing. In a team, this is like your group project, 7 people working together in a room trying to do something. So how many people have had this happen in their group projects then? You show up one morning, someone has changed something in the code and they've broken it all and no one admits to it and you can't track down what actually happens or who to blame. Does this still happen to everyone? Yeah? Is everyone else using nice source control systems to prevent this to some extent? Okay, so how do you prevent this from arising? Okay, the traditional solution, which I don't recommend, is one person, one unit. Okay, a traditional software team, you say, these are all the bits of the system. Each bit is owned by a person. It's your problem to make it work. You write the code. No one else is even going to look at the code that is owned by you. It's your responsibility to make that thing work. Okay? Sometimes described as no man should have to look at another man's code, or woman, or gender-neutral person. In this approach, then, you are completely responsible for what is inside that unit. Other people can see the interface, the API, and that's how you're going to communicate. So problems with this is that it doesn't scale. As the code gets big, one person can't maintain all that code. You can resolve this by cutting it into pieces, and the maintainer of that unit can then give each subunit to someone else and give them responsibility like that. The owner may be on vacation or uncontactable when something goes wrong. No one else knows how the code works. Or they may be run over by a bus, which is standard speak for leaving the company, leaving the team. And again, there's no one else who knows how the code works. So for those reasons, we don't usually do that nowadays. What we do instead is we use unit tests as contracts to allocate blame. So we still say each unit in the code has a maintainer. Let's say this is you. So here are the units. Maybe this is my unit. But now I do allow anyone else to see the code and to edit the code. This is more like a Wikipedia approach to coding. Anyone can come and contribute stuff. Now, to maintain sanity in all of this, I don't just want people to go off and randomly change my code in ways I don't understand. So what I do is I create a set of tests to wrap my code, and I say, I will take edits from you if and only if they continue to pass my tests. Okay, so you go and fork my code, do whatever you want with it, send me a pull request only when the thing is passing the test. And there are automated systems that do this as part of the pull request now. You sometimes get a thing that says, here is a pull request, and by the way, it has passed all your tests. So if someone sends me something and it passes all the tests, then I'm probably just going to accept it. If it doesn't pass the test, it is their problem to make it pass the test. If it enters and still passes the test and something goes wrong, then it is my problem. That means my tests are not good enough. I've not defined the right tests to give the behavior that I want. And this approach can really scale. This scales to open source projects with thousands, tens of thousands of members working together. Okay, so let's consider a unit test as a special case of this more general contract-oriented idea. A contract just means any promise you're making about the interfaces, the boundaries of your code. You're going to promise some property of the inputs and the outputs and the relations between them. So a unit test is one particular form of a contract, okay? A unit test is a promise that if you call my add function with the specific numbers 2 and 3, then I promise my function will always give you 5, because that's exactly what that unit test is testing. Yeah? If you have a unit test that says 0 add 0 must equal 0, that's another promise. But it doesn't promise anything more general than that. Let's consider other things we could promise about both the inputs and the outputs. Okay? If you're using a language that has types, a strongly typed language, this will often enforce type promises. So for example, you can promise that the output of your function will always be an integer or a float. Okay, this does not happen in a language like Python, where you can chuck anything in and out. More strongly than that, you might promise particular properties of your inputs and outputs. So for example, you'd have difficulty doing this in a regular type language. Promise that the output will always be an even number. Okay, so you can, with a language like C, you can promise that the output will be an int. It's a little harder in C to promise it will always be an even number. There are languages where you can shoehorn this into the type system. So for example, in Haskell, it's very heavily typed. It has a much more complex type system than C. And in Haskell, you can create entities called type classes, which will do this kind of thing. You can consider the type of all numbers, of all integers that are even. Or you could consider the type of all vectors where the sum of the elements is 10, and this kind of thing. So sometimes you can shoehorn all these contracts into the type system. You might promise that the output will always be a particular function of the inputs. So that's the idea of a specification that we saw. So there's a difference between an imperative program that adds two numbers together and a logical promise that output is identical to input A plus input B. Okay? That's the difference between mathematical equality and imperative assignment. You might promise that certain things are invariant. Some languages have keywords like const or constant, which say, I promise not to touch this thing. You're going to pass me this data, but I'm not going to mess with it. We can also make contracts on the input. We can condition our promises. So as an author, this gives you a get out clause. You can say, I promise I'll do all this to my outputs, but only if the caller promises for certain things about their inputs. So you can say, my promises are only valid if your input is an integer. Again, that's something that the type system could be used to handle. Or we could say this is only going to work if the input is an even number. So again, you could do that with Pascal type classes. If you work in database systems, this is a very common one. I'm only going to do this if your input is some kind of sane string that doesn't contain any malicious code. If you call me with any of these inputs, I'm either going to throw an error or I'm just going to blame you for any bugs that come out. So here's how you do more general contracted-oriented programming in a language like Python. Okay, so here's my addition function. You can see this is imperative addition. I'm doing operations on this thing called result, and then at the end I'm going to promise that the thing I return actually is the sum of the two inputs. Okay, and again, this is an assert function. Assert will throw an error if the statement is false. So look, you can make your own type system with contracts. Okay, so Python isn't a very strongly typed language usually. But if you want to do type-based programming, you can. You can say, I'm only going to do any of this if you promise to call me with an integer x and an integer y. And I'll promise you that my output is also an integer.
Do that with the type hinting in 3.8 as well.
I know. There's a general drift back towards this stuff in a lot of language design at the moment. So yeah, this is roughly equivalent to this kind of thing, right? This is what they're talking about putting back in now. But you can do more general things beyond the regular type system, right? You can say my square root function is only valid if your input is greater than 0. That would be a little harder to catch with a type system. Yeah? Floating point number, but greater than 0. Yeah, there's various approaches to it. So what you get in contracted-oriented programming then is a bunch of asserts at the beginning, a bunch of asserts at the end. And we're going to do this deliberately as a software engineering practice, and we might have special tools that understand what these things are and are able to process them. So for example, you might have a documentation tool that will pull out all the promises for inputs and outputs. So look, here's an auto-generated doc for my addition function. Okay, it pulls out the comment, and instead of just promising what the types of inputs and outputs are, it pulls out all the contracts. You're saying this function only works if x is an in and it's greater than 0, and y is an in and this is greater than 0, and these are conditions on the output. Now, if anyone's code is incompatible with anyone else's code, we know exactly who to blame. We know, was it the person calling the function, or was it the implementer of the function? So, contract-oriented programming is a cool concept because it unifies two things that you might not have considered as parts of the same concept before, and that is the type system of your language and the concept of unit testing. Okay, with the idea of a contract, we can look at both a series of unit tests and input and output type checking as different instantiations of the kinds of promises we can make about the inputs and the outputs to our functions. And we can then generalize those promises, even to include things like formal specification systems, to make any kind of promise about what's going in and what's coming out. And it gives us a way to figure out who to blame. If there's a breach of an input contract, it's the caller's problem. If it's a breach of an output contract, it's the implementer's problem. You can use this in your team working, but also with your own code, just to keep track of which function is responsible for what, rather than which person is responsible for what. Again, when we consider testing as part of a contract system, we always have to bear in mind that test contracts cannot cover every case. They are weaker than these formal logical specifications. So for example, if I write my add function like this, I've made a bug in my add function. What's the bug in my add function? Yeah? I'm not doing addition. I'm doing a multiplication because I pressed the wrong button. I did multiply instead of add. So I've made a bug here. This implementation is still going to pass these tests. Okay, if I chose 2 plus 2 equals 4 and 0 plus 0 equals 0, both of those tests are going to pass, and my bug is still going to survive through that testing regime. This would not be the case if I wrote my contract using a logical specification instead of using a unit test. So if I say something like this, for all input X and all input Y, the result of adding them together is in fact going to be the sum of the two numbers. Okay? Now, this is much harder to prove. With tests, you just have to run the function. This is a form of dynamic analysis. So you run it, does the result come out? Yes, you're good. Proving specifications like this is much harder. This is going to require advanced static analysis, and it's going to require a lot of very real computer science. You're going to have to reason about the objects in your program to actually demonstrate this. This is a theorem about how a particular program is going to behave. A nice project for anyone looking for a third-year project idea, by the way, would be to try and write a deliberate, malicious, maybe machine learning system which learns to pass unit tests. Okay, if I give you a list of these unit tests, and some commercial companies operate in this way, if they're doing test-driven development, they will write all the unit tests before the code as a type of specification about what the code should do. They will then delegate the work to you as a junior employee, and you get paid if and only if you pass all the unit tests. Okay, so a fun third-year project for someone would be to write a machine learning system that learns to pass unit tests. Okay, I could give you these unit tests to describe the addition function. You could then plug these into a deep learning neural network or your favorite malicious system, and it will come up with something that will satisfy those particular unit tests. If you do that, it is very unlikely that your function will actually generalize what was intended. So, for example,
could you do that with programs as well? Well, I suppose it would be like a subset of that, but you already have. The main one I think of is there's a scheme interpreter where you can give it the specification and then it will output something which satisfies that. And if you have a certain, you can alter certain aspects of it so that it must have certain things so that it will be what you intend it to be. But if you just kept it as that, then it would.
Yeah, so there used to be a research area called genetic programming. Again, a very lispy thing. You can evolve programs, you can operate on the programs, move things around. Yeah, you could use whatever approach you like to try and pass a bank of unit tests. If you could do that, you could possibly make a bunch of money. You could go on these contractor websites and agree to deliver code for all these people who've specified what they want as a set of unit tests. Press the button on your system, off you go. Okay, so a variation on contracts in contract-oriented programming is the concept of a validation function. So you might have come across these, especially if you work with databases. When you do contract-oriented programming, your contract will usually just throw an error and stop if a contract gets violated. Okay, so you might, for example, have a function like this. This is going to find an employee in the database. Here there's an input contract saying the name must start with a capital letter and the second letter must be a lowercase letter. That's part of the contract for what a name is supposed to look like. If your name doesn't look like that, I'm just going to stop and complain on it. It's your problem to go and fix it. So sometimes, especially if you're dealing with input from users, if this was part of a web-facing database system connected to a web form, you might not want to be quite as heavy-handed as that. You might want to do what is called a validation function instead. This is a more benign variation, where instead of just barfing when a contract is violated, you actually come in and try to fix it for them in a sensible way. So in database systems, you'll often find things like this. You'll see the name comes in and the name gets validated. And the validation function is going to try to ensure that the name meets the requirements of the contract. So for example, here we call validate on the name and it's going to actually enforce, it's going to make the first letter an uppercase letter and the second case a lowercase letter. So the classic application of this is to do with SQL injection attacks. Have you done this in databases yet? Or you'll see it, yeah? SQL has some problems with the language itself. It's possible to do very bad things by inserting bits of SQL commands into queries. So if the designer of a website is not doing this validation correctly, you can have scenarios like this where you type in your name into a web form, and as part of your name you put in a quotation mark and a bunch of SQL, which might delete the entire rest of the database, and that can go through and get executed. So it's very common in database programming to have these validation functions. Again, there's a software engineering lesson here, because database programmers will look down on people who forget to do these validation functions. That's seen as a sign of being a bad programmer. When you think about it, this is actually kind of dumb, because when we design programming systems, we want to reduce that kind of cognitive load. We don't want people to have to go off and do boilerplate stuff all the time. So again, you might use static analysis tools at this point. You might, for example, run a linter which checks that everything in the program is doing that validation as a way of automatically finding those errors and vulnerabilities. And this, again, is an example of the duality between software engineering and language design, because if SQL itself ever gets upgraded, SQL is a glacial language. If it ever gets upgraded, this is almost certainly something that will be looked at, because this was really a bug in the language itself. If you find yourself relying on linters for this kind of thing, it suggests maybe something needs to happen in the language to really fix this. So, test-driven development. We've touched on this a little. This is a modern trend of writing a bunch of tests, maybe not all of them, but writing a bunch of tests before you write the code. Not only for giving work to subordinates, but as a way of shaping your own programming practice. Is this a good idea or not? There is remarkably little empirical study in software engineering. I'd love to tell you that 90% of all test-driven development projects work better than ones that don't use it, but there's very little data on it. It seems to be something that many people currently consider a good idea. I would really ask these questions. I'd say, remember that unit tests are part of this more general idea of contract-oriented programming. So, is writing a set of unit tests the actual best way to specify what you want this function to do? Remember, we've seen other forms of contract as well. There are forms of contracts around type systems, around relationships, and around formal specifications. So really, writing a formal specification would be a much stronger way to specify what you want. You could say, for all inputs x and y, the output is going to equal x plus y. And that gets you back into debugging the specification. You're going to often end up with specifications that are much longer than the program you write. And when you make the specifications contain so much information, if the specification of the add function is that z equals x plus y, why not just use that as the program? And that's exactly what you get in higher level languages like functional programming languages. A functional programming language, you basically program in specifications, and it automatically turns that into an imperative program running inside. You will typically find if you use a functional language, there will be much fewer bugs in everything. You'll have different kinds of issues. You'll have to think a lot more about the design. You'll often find your program doesn't compile in a functional language, but it's a much more pleasant experience to fix compiler errors than it is to spend your days inside a debugger. Functional languages were, when I was an undergraduate, they were esoteric academic things that people used to laugh at and say, this is a reason why university education should change and be more industry focused and teach C like everyone's actually using in the real world. And now 20 years later, everyone's now decided that what those academics were researching was actually a pretty damn good idea. And Haskell is becoming a big thing and is getting used in billion-dollar hedge funds and all this stuff to reduce errors. If your C program executes in a hedge fund and some memory error means you lose $10 million, that's really not very funny for the person who does it. And it's an excellent use of a more academic language that doesn't have that kind of bug in the first place, if you're able to prevent it. So maybe test-driven development is just one instance of something more general. Maybe we should think of contract-driven development. This is my own term, as encompassing all of these things: unit test-based specifications and typing and formal specification and proof. Okay, so we've looked at a bunch of static analysis tools. We've looked at unit tests. These are your main defenses against bugs creeping in. If all else fails and you're still left with a bug, now you may have to do some actual debugging, okay? So debugging is another form of dynamic analysis. That means we are going to partially execute the program, as opposed to static analysis, which is just making inferences based on the text of the code. Debugging is hard, okay? Brian Kernighan said, debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it. Don't write clever code. Don't do weird stuff in C. Write code so that people can actually read it. So debugging occurs when you have written and run your program and it is not working. And now you have a problem, right? We all know debugging is dirty, it's time consuming, it is mentally straining, stressful, and generally a bad thing. Like war in the art of war, the best way to do debugging is to not have to do it. You want to set up your life so that this just isn't even an issue. And you're going to do that by using static analysis tools and unit tests primarily, and contracts in general. So, if you are struggling with bugs in general, maybe you have a problem in your programming life. Maybe you should think a little more about the kinds of tools and methods you're using in the first place. Maybe you should think about putting more contracts into your code. That includes using type systems, unit tests, other assertions. Maybe you should use a language which just rules out large classes of bugs, specifically languages like C, which allow bad things to be done with memory access. Even if you need to do memory access, we now have Rust, which has been specifically designed to do all the stuff that C can do, but removing a whole load of possibilities of those kinds of bugs coming in. Maybe you should consider using a functional language like Haskell. The other property of functional languages is they have much less state. A language that is purely functional does not maintain values of variables other than on the core stack. And we will see that the size of your state is intimately related with the effort that it takes to do debugging. So in a functional language, this is all going to be much easier because there's less state. General concepts, think about algorithms before coding them. Are you really using the right algorithm? Can you prove theorems about your algorithms before you bother to code them up in C? Because if your algorithm doesn't work, then it's a lot easier to catch it at that level before you get to the code. But when you really must debug, let's spend some time studying this, because people do spend, in some cases, 90% of their lives as programmers doing debugging. Let's spend 10 minutes on it at least. So the debugging process is actually quite an interesting object of study in itself. Debugging is a science. It uses the same scientific method that we use in science, in physics, biology, and the same scientific method that is used in fixing your motorcycle or your central heating system. So, what is the scientific method? Roughly, it is this. The world may be in one of many possible states. We call these possible worlds, and you don't know which state the world is in. If you knew which state the world was in, you would instantly know the answer to everything. So what you have instead is you have some limited data about what's going on, known as observations. The rest of the state of the world is hidden from you. And as a scientist, you can make hypotheses. So hypothesis is just a guess. You can guess that something is happening in that hidden part of the state of the world. In this case, the cause of what is going wrong. Usually you can't go and observe whether your hypothesis is true directly, but any hypothesis will create predictions. So if you make a hypothesis that objects fall to the ground, that predicts that this mouse will fall to the ground when I drop it, and that's something I can do an experiment on and I can observe. So at this point, we design and run experiments to test predictions coming from our hypothesis. Those experiments give us more information, and the information formally reduces the number of possible worlds that are consistent with what appears to be going on. So again, I talked about states. There's a number of possible worlds that we could be in. One of them is the world we're actually in, and our job is to find that world to understand what's going on. Every time we do an experiment, we make a hypothesis. The experiment gives us some data, and that reduces the size of this possible world state space. Ideally, we want to cut it in half every time. That'll give us an optimal search algorithm to cut down the state space. So we're going to repeat this and make the state space smaller and smaller every time we go around. So Zeller has done a lot of work on the academic concepts of debugging. This is his book, very nice book. I suggest you all read it. One of Zeller's contributions is giving more precise terminology for what's going on in debugging. When we talk about a bug, we throw this word around as if a bug is a discrete thing. That when you think about it, the bug breaks down into certain other parts. So when we're dealing with a bug, we're dealing with these concepts. We're dealing with the state. Okay, in terms of computer science, the state is roughly the state of the computer's memory at each point in time. This is actually quite difficult to define on a modern machine. If you're running a machine with an operating system and all these other processes going on, sometimes you want to consider the state as only the state of your process. The really nasty bugs are when your process is interacting with other parts of the system. Then you've got to consider the whole state. So then we consider units. This is the same units we've met in unit testing. So a unit is any reasonably identifiable chunk of your program, often existing in a hierarchy. And units are interesting because when we do bug hunting, we're going to try and isolate where the bug is within that hierarchy of units. So the units can be thought of forming the basic state space, and we're going to try and rule out which units may have the bug and which might not. And then Zeller separates out the defect from the failure. So the defect is the cause of the bug. That's the thing you're actually trying to fix. You're trying to find it and you're trying to fix it. The failure is the observation that you actually see. That might be something like an error message or weird behavior or even the program not compiling, or ideally it's your test failing. We can then consider different forms of defects. And these are basically categorized by blame allocation. Okay, so a defect may be caused by a programmer error. So when I wrote my add function with a multiply instead of add, that was clearly a programmer error form of defect. There could also be a user error. Again, today all our programs call other people's functions, and if you're not using contract orientation, it's very common for a user to do something that they weren't supposed to do. The implementer of the function might have said this thing only works for integers and you've called it with a float. And if there isn't a proper contract in place, then this is a form of user error. If you have a contract, it's very easy to catch these things. And then probably the most common form of defect nowadays is what we call a glitch, which isn't really anyone's fault, it's just a general misunderstanding. Again, systems today are very complicated. They have to interact lots of different people. And if you have a class cat that you've written that is supposed to represent cats, and your friend calls it, assuming that all cats have 4 legs, but you decided that some cats only have 3 legs, or there has to be some special case. There's often just some misunderstanding. You can't blame either side, it's just that the formal specification wasn't completely worked out. So again, contracts will help you a lot. If you have contracts in place, maybe these bugs will just never occur. So then we have terminology about the location of the problems then. We say a program is infected, or it's in an infected state, in the time period in between the defect occurring and the failure being observed. Now in some programs this can go on for a very long time. Okay, so you're writing a game and something happens and some character ends up in a place they're not supposed to be. 10 minutes later that may have a knock-on effect that something weird happens, and that's the time that the user sees it. So for that whole 10 minutes the program is in an infected state. So we can also localize state in space as well as in time. And this is based on the concept of units. We can build that hierarchy of units and say which parts of the program are known to contain the infection. That's called the infected state, and which parts of the program are known to not contain the infection. That's called the sane state. And then there are other parts of the program that you don't know if they're infected or sane. So again, that's a lot of words, but having this vocabulary around helps us to be much more precise when we're dealing with bugs. So what we're trying to do during debugging then is to try and reduce the size of the infected state, to home in on the thing. Okay, the state is usually the state of the computer's memory during the infected time. So here are all the parts of my program. Every time I do an experiment to test what's going on, I can bisect it. Okay, so the first bisection I've done is this line here. I'm saying, is the bug there or is it in the bottom half? And in this case, it's in the bottom half. Then I say, I'm going to cut the bottom half in two. I'm going to design a new experiment that will rule out the bug being here. So I colour it green there, and all of this will go red. Then I bisect this, and this goes red and this goes green. I've done, the last bisection I've done is here, and I've now isolated the infected state to this region. And hopefully this region is now one unit of my code. So, there are formal information theoretic ways of dealing with this. You can say, how much information do I get from each experiment? If your experiment is a yes-no experiment, so very often when I debug your code in workshops here, we'll try something out. We'll say, what happens if we change this to 0, and the program either works or it doesn't? That's often the case when you're using the universal fix-everything algorithm. Okay, you have one working version, one non-working version, and you're going to partition it so that this test version of your program is either on the working side or the non-working side. So often you'll only get one bit of information from an experiment, and one bit of information is sufficient to bisect the search space for where is the infection. Other types of experiment will provide more than one bit of information. So for example, if you print out a whole load of numbers and state, that gives you more bits of information, and that can help you more rapidly isolate where the infection is taking place. So again, this is why functional programming is a good thing, because functional programs, especially pure functional programs, have very low state spaces. So they still have state in terms of the call stack, but you don't have all these variables sitting in memory containing values that give very large state spaces. So this is going to take you longer if you're using lots of variables in memory than if you do everything in a functional style. So how do we come up with these experiments? How do we know what to try? We are faced with a failure. We are trying to find the defect, and we are trying to create an experiment that gives us information to reduce the size of the infected state. So this is the scientific method, okay? As in the regular scientific method, there is no obvious algorithm for doing this. What we have instead are heuristics. Heuristic is a Greek word. It means vague rule of thumb that seems to kind of work sometimes, but we don't really know how or why. So there are approaches for guessing hypotheses that help us create these experiments. I've divided them roughly into two types. There are targeted hypotheses. This is where you guess a particular defect or something very close to the defect. You're going to say, I really think the world is in this particular way, and I'm going to go out and test, is that true or false? Versus information gathering experiments. This is where I say, I don't really know what the cause is, I'm just going to try and bisect the state space into two by doing some more general experiment. So this is a similar process to the game of 20 questions, right? I'm thinking of a person. You can ask me 20 questions. So you could make a targeted hypothesis. You could say, am I thinking of Isaac Newton? Okay, if you've got a really good idea because you know all this stuff about me, and Isaac Newton's the sort of person I almost always pick in the game of 20 questions, that would be a targeted hypothesis. Now the advantage of that is that if you're really confident, you could find the bug immediately in a single question. The disadvantage is most of the time it won't work and you'll have wasted one of your questions. So an information gathering question is more like, is the person you're thinking of, I'm not allowed to say male or female anymore, am Is the person you're thinking of, do they self-identify as a male or not, which will give you an approximately 50-50 gender-based classification. And with that type of information gathering question, you will gradually bisect the search space until you find the thing you're looking for. So, how do we come up with these then? To come up with a targeted hypothesis, this is going to come really from your high-level understanding. If it's a program you've written yourself, you know what the program's supposed to do, you know the underlying computer science algorithms of it. You can look at the data. As you get more experience in your career, you will tend to see the same types of errors, the same types of failures, and you will build up what is honestly an intuition for just guessing. Your brain will perform pattern recognition like a neural network. You will see a particular failure and it will just subconsciously trigger a guess about what the cause could be. To come up with information gathering hypotheses, you're going to be a little more conscious and a little more strategic, and you're going to really think about how can I cut the possible states of the world into two in the most efficient way. So to do this, you might, for example, put in lots of printfs. You might just print out lots of variables in the code, and that will give you information about what is going on. This is especially useful if you write functions for every class in your object-oriented system called toString, which gives you a nice string-based representation of each class in a pretty format so that you can easily print out everything that's going on. Another way to do this is to walk through your code. You can use a step-by-step debugger and execute one line at a time. This will give you lots of information what's going on. And in particular, this may help you to isolate the infection state over time. You might see additional failures. If the only thing you knew about the failure was that 10 minutes into the game this thing goes wrong, when you step through the code you might notice something extra happening only 2 minutes in, because you know this variable should have been 0 and it's actually 5. Many debugging systems have something called a watch function. This is a refinement of these printing out lots of data functions, which when you do a watch it will only print out a variable when it changes. So if you just print out every time, it'll say x equals 0, x equals 0, x equals 0, too much information. A watch function will only print x equals 0 once, and when x becomes 5, it will tell you that it's become 5. So in this approach, you've really got to think about this and say, which regions of this program state am I currently believing could be infected, and how do I design experiments to cut that in half, ideally? Now, a really good way to cut your infection state in half is by adding more contracts to the program. Okay, instead of just stepping through your code, this is really what we're trying to get away from. If you take one thing away from this lecture, it's don't spend your lives in a debugger, stepping through a line at a time. A much better way of implementing these hypotheses is by adding contracts, including unit tests, but maybe the other types of contracts as well into your code. So you have a question. You know, I don't know if x has turned into 5. Maybe the bug is to do with x being 5 when it should have been 0. So instead of just stepping through and looking at x or printing out x, what I'm going to do is I'm going to write a contract, which might be a unit test, and I'm going to say assert that x is actually 0 at this point, because x should always be 0 there. Now, I might do this on a command line, I might do it in a step-by-step debugger, but when I've done that, I'm going to add it to my unit test file as well. The idea is that we're going to have this great big set of tests, and every time we test anything, we're going to keep contributing it to that file, because that unit test file is going to be very useful to everyone who ever works on the code in the future as well. This is going to help other people find their bugs, making sure that they pass the same contract. So that's my preferred way of doing this. Add lots of contracts to everything. So other ways to test things, you might just print things out, you might put in a bunch of printfs, you might watch things, you might just step through a line at a time. But I'd really suggest now that if you're doing these things, think about also, even after you found the bug, just quickly make a unit test that wraps up the thing you just found out and shove it in your file, and that will help everybody else in the future who has to work on the thing. So, okay, this is the inner circle of hell. If everything else has failed, this is where you find yourself. So here we are inside the debugger. You really don't want to be here, because you should have been using all the other stuff we've talked about first. If you find yourself here, this is what a debugger looks like. So this is GDB. which in this case I'm debugging a C program, I think. There are similar debuggers for most languages, and they all tend to use the same commands. So I have compiled my program with debug information, I have run it through the debugger, so I can step through a line at a time, execute this line of the program, execute this one. I can say print out a backtrace. If I type VT, that will tell me all the function stack that's been called. I can step through, I can either step over the lines or I can step into the lines. So if a line of my code says call function add, I might want to go into that function and see how the add function works, or I might want to step over it by treating it just as a single line. So I can return from a function by pressing R, I can print out a variable name. In the better debuggers, I can call arbitrary functions that do affect the state of the program. So this actually gives me a command line. If I just want to make the value of x equal to 5, I can actually set it as that and then go on running the program again. Not all debuggers will let you do that. There's a lot of good computer science in setting this stuff up under the hood. We can set a breakpoint. That means run the program up to line 100 and then stop. You can often set a conditional breakpoint. So that means stop at line 100 only if x equals 0. That's very useful if your bug is inside a loop and you want to say run the loop until the 37th iteration and then do a breakpoint. Sometimes you will write parts of your code to make it easier to debug. So you might have a loop and you want it to stop on the 37th time. So you're going to say in your code, you say if I equals 37, print hello, and then you set a breakpoint at the line that prints hello, and that will get the loop to stop at the 37th iteration. So it's worth learning to use GDB even if you don't program in C, because the other debuggers all tend to be based upon it. They all tend to use similar commands, and that gives you a general language for controlling debuggers in general. So what's happened here? Look, I've typed info breakpoints. This tells me there's one breakpoint set and it's set on line 4 of the factorial function. That's where the program's going to stop. So then we run the program, we've hit the breakpoint, execution has stopped at line 4, it's printed out the source code corresponding to that line. Remember, the program you're running isn't the source code. The program you're running now is a load of machine code. So there's some very clever computer science that has gone into tricking the system into making it look as if you're really running the source code. And so on. We could print out the values of the variables. We could go in and change the state of the program. We could watch things, try and find the bug that way. So debugger design. Maybe that wasn't the innermost circle of hell. This is the even more exclusive innermost circle of hell. This is designing the debuggers themselves. If you really want to get into this, Rosenberg's book is amazing. He wrote one of the, I think he wrote it for Turbo Pascal or something, the graphical debugger. He's the only person I know of who's actually written an academic book on what the hell is going on inside these programs. And it is disgusting. What you see in a debugger is a complete illusion, right? Your real program is a bunch of machine code that runs on a CPU, and it does all the stuff that we learned about in computer architecture last year. So tricking the thing to look as if it's running a line at a time of source code and then stopping and returning control to the user to give you this information is a very bizarre thing to be doing, and it's all smoke and mirrors. It's about providing the illusion that you are executing the source code. So in some languages, you actually do execute the source code. As far as I know, Scratch is working like this. I showed you a Scratch program earlier. As far as I know, the Scratch system actually takes each line of that program and then does something with it and does something else, like a very, very pure interpreted approach. But usually, a piece of source like this is going to get compiled into something utterly unrecognizable as machine code, and the point of a debugger is to retrospectively make it look as much like that as it can. So in particular, a compiler will turn all your variable names into memory locations. It will turn all your function names and function specifications into machine code. You will lose all the structure. So an early form of software engineering was the introduction of structured programming. This is the idea of having curly brackets around everything instead of using go-tos. When you're at machine code level, you're back to using go-tos again and jumps. So all of that structure that was lost by the compiler has to be illusionarily restored by a debugger. So you can get some insight into this by doing an object dump. you will have to compile your code with a special flag which says include some extra information in the machine code. So your basic machine code has lost all the information about these variable names and structures and everything. When you put in a flag like this, GCC-G, that will include some extra stuff that is designed to help debuggers see what's going on. If you run the tool obj dump, that will give you some insight into some of the magic going in there. When you get into changing the state of the program, there's even more magic, and there's always what is called the Heisenberg principle, that the debugger might change the execution of the program, especially things around timing, inter-process interactions. Things get even worse when you're debugging from other people's error reports. Okay, normally when you debug, you can see the failure. Remember, there's the defect causes the failure, and that's your process is to guess, hypothesize the defect from the failure. When you're dealing with other people as users, you don't even know what the failure is. Now you have to do the scientific process again to guess, hypothesize what is the failure before you can even start looking for the debug. So this is where educating users is always good. I mean, you get something like this. Hi Charles, I tried to run your Music Genie thing, but it's not working. It just prints out a load of crap instead of showing the GUI. Please, can you fix it? Thanks. Like, what am I going to do with this bug report? Probably not very much. Okay. Whereas, here's a nice user. This person has filed something on a proper issue log. I tried to run Music Genie from the master branch on this date, this version. This is my system spec. This is the version of Java I'm running it on. This is something I can actually work with, right? I could probably set up a virtual machine with that configuration and be able to reproduce. And look, they've even given me the line number where the thing came from. I can fix that in a few minutes. So debugging from other people's reports is a whole other kettle of fish. Sometimes you need to debug post-mortem. This is if your program crashes, it creates a file called a core dump. A core dump is a snapshot of all the computer's memory. That enables you to reload the core dump, attach your debugger to it, and then get inside and see the stack trace and everything. So again, some nice users will send you a copy of the core dump. This may be quite large. Sometimes core dumping is used humorously. If I just core dump at you, I give you all this information with no filtering. Sometimes that's the only way to do it. Reverse debuggers are a thing. They have been in the wild for a long time now. Not many people still know about it. So we built one as a group project last year. We built a reverse debugger for ARM assembler in David Churchill's project, which lets you click through this assembly program like you did in Mari in architecture and then click the back button to rewind it. Again, lots of magic in that. This stuff is standard in a debugger like GCC now. You can just type backwards to go backwards in GCC. Not a lot of people know that, but it is there. Concurrent debugging, just don't go there. Just don't. Or do a PhD in it first and then come back and tell us how to do it. If you're faced with concurrent debugging, for the love of God, just find some way to make a non-concurrent version of it and fix the bug in there. The best book ever on debugging is Zen and the Art of Motorcycle Maintenance. There are long sections in this about the process of fixing a mechanical motorcycle system and the thought process of making the hypotheses and dividing the state space. Very, very beautiful book. If you like Gödel Eschebark, you probably like Zen and the Art of Motorcycle Maintenance as well. There are other types of dynamic analysis. In the bad old days, we had to use memory monitors to check for memory leaks. In C-like languages. Again, do we really need to do this now we have Rust? Rust will protect you from all these things in the first place. There are profilers. This is another type of dynamic analysis that counts how long your program spent in different functions. Tells you how many milliseconds are in each function. So if you want to make your program go fast, it tells you which bit you need to optimize, which is almost always not the thing you thought it was going to be. So it's really important to run a profiler before you start going in and optimizing. General lessons of bug prevention and removal. Then. It's all about trade-offs, okay? It's all about language design and software engineering and the inherent trade-offs. Should you choose a language or a software engineering process that encourages rapid prototyping versus technical debt, okay? If you use a language like Python, you don't have to spend your time putting in contracts like type information. That means you can build your prototypes very quickly. The downside of this is Python was recently described as a credit card for maxing out your technical debt. Okay, you very rapidly build up all these things that could go wrong, and at some point, someone is going to have to go in and write those contracts. It's just you didn't do them at the time you started. So there's a balance, right? Especially when you do scientific computing, you need to go fast. You need to use the thing like a calculator. What we're seeing recently is this incremental adding of contracts. Maybe the idea that you write it and if it works, you leave it, but then when you get to debugging, instead of getting in your step-by-step debugger, you put in the contracts at that point as part of your debugging process, and then they stay there, and then they won't happen again. So similarly, you've got this trade-off between the power of your language versus the ability to rule out large classes of bugs, okay? You might think you really want a powerful language. Look how macho I am. I write raw C without using protection. That's really not a good idea nowadays. You might be so macho you can do that without bugs, but you will make bugs, and those bugs will take time and effort to fix. Can you restrict the language? Can you use a high-level language? Can you use something like Rust with that stuff built in? Could you use a functional language where it isn't even an issue? Again, language design versus software engineering tool. One man's software engineering methodology is the next man's language design feature, and we tend to see, again, a language like Rust will take what is considered good software engineering practice and just bake it into the language. The single message of all of this is what I've learned in all my own programming career, which I wish someone had really beaten into me with a big stick, is bug prevention versus treatment and cure. You should not be spending your time in a line-by-line debugger. If you find yourself doing that, you have a problem. And it's okay to talk about it now. We can talk about it in the open. Make sure you know about these techniques and try and put yourself in a more hygienic situation in the first place where these infections just don't occur. Thank you. See you next week.